Good morning. Let's start our lecture today. So last time we were trying to solve equation t to power 4 x power fourth derivative plus 60 to power 3 x3 plus 70 x second plus t x prime minus x is equal to 0. Alright, so this is the equation that we were trying to solve last time. The method is again to use an ansatz of the form xt is equal to t to the r. Right? So then what we found is r is equal to what? What did we find last time?
We found that one solution was r is equal to 1, and then we were continuing to factor the problem.
Yes. Right, so I don't. Yes, okay. So, yes, thank you. Can
Yeah, absolutely.
So then when we plug this into the equation, we have r minus 3, r minus 2, r minus 1, r plus r minus 2, r minus 1, r plus r minus 1, r. There's a 6 here, right?
Mm-hmm.
There's a 7, r minus 1 is equal to 0. Thank you. Right, so in the previous class, we choose the solution to be of the form t to the r. We plug this solution into this equation, right? And when we plug this into the equation, what we found is something like t to the r times r minus 3, r minus 2, r minus 1, r plus 6 times r minus 2, r minus 1, r plus 7 times r minus 1 r plus r minus 1, right? Now, this is nice because you can draw now t to the r and you get a new equation, which is an equation that do not have t, all right? And then you have a characteristic equation. Since it doesn't depends on t. All right. So when you choose the solution to be t to the r, you plug it to the equation. You get an equation of r only. So in this case, you have a characteristic equation because the new equation doesn't depend on r on t. Right, so now let us try to solve this equation. One thing that you can see is that here you have r minus 1, r minus 1, r minus 1, and r minus 1, right? So I can put r minus 1 to be a common factor, and I get the following equation. So I have r minus 1, r minus 3, r minus 2, r plus 6 times r minus 2, r plus 7 times r plus 1, and this is equal to 0. All right? So this equation, now you have to solve this characteristic equation. When you can solve, if you can find all of the r that makes this equation 0, then t to the r should be the solution. All right? This equation has a special structure because you can put r minus 1 outside as the common factor, and the leftover is r minus 3, r minus 2, plus 6 times r minus 2r, plus 7 times r plus 1, right? Right, so now one solution is r is 1, but let's try to factorize the other term. So this one gives you r squared minus 5r plus 6r, and this is r to the power 3 minus 5 times r squared plus 6r, right? So now I have to develop all of the terms and I group them together. So you have r minus 3, r minus 2, r is r squared minus 5r plus 6. You multiply that with r, you have r3 minus 5, r2 plus 6r, right? Now, the next term is 6 times r minus 2, and this is 6r squared minus 12r. All right? So now I add everything. Right, so I add everything. So I have r minus 3, r minus 2, plus 6r minus 2r plus 7r plus 1 is r3 minus 5r squared plus 6r plus 6r squared minus 12r plus 7r plus 1. Right? So what? How can I simplify this expression? Yes?
You can combine the like terms and then you should get r cubed plus r squared plus r plus 1.
Yes. Can you sign the back paper, please? So this is r cubed. There's no other terms, right? So I put r cubed here. The next one is to combine 5r squared plus 6r squared. So I have r squared. The next term is this guy, and this guy. So I have r, right? And the last one is this one. So you have r cubed plus r squared plus r plus 1, right? Right. So now I put that one into this equation. So I have r minus 1, r cubed minus r squared plus r plus 1 is equal 0. All right? Questions? So what is the next step? Yes?
If you factor out an r squared, like so it'd be r squared, r plus 1, and then r plus 1.
Yes, can you stand back by please? Yes. Can you stand? Right. So now we continue to factorize this polynomial, right? So you have r cubed plus r squared plus r plus 1 is r cubed plus r squared plus r plus 1, right? So I'm going to group the first term and the second term, and the third term and the last term, right? So I have r cubed plus r squared plus r plus 1. But r cubed plus r squared is r squared r plus 1 plus r plus 1. So I'm gonna have r squared plus 1 r plus 1, right? So finally we get an equation. R minus 1, r squared plus 1, r plus 1 is 0. So the first step is to put out the r minus 1, which is easy. The next term is r cubed plus r squared plus r plus 1. You can factorize it using the factor r plus 1. So the last term is r squared plus 1. Right? So what are the solution of this equation? Yes?
Is it I and -1?
Therefore. So this equation has
plus
from
or minus I, -1,
and yes.
Oh, and 1.
Yes. Can you both sign the back paper, please? So in this equation, you have what? You have r minus 1 is 0, meaning that r is 1. This is one solution, right? R plus 1 is 0, meaning that r is minus 1. So this is the second solution, right? And the last one, so you have r squared plus 1 is 0, which means that r is plus or minus I, right? So then you have 4 solutions. So we have 4 solutions. So R1 is 1, R2 is minus 1, R3 is I, R4 is minus I. All right? So the characteristic equation has 4 solutions, plus, minus 1, and plus, minus I. So what are the solutions of the differential equation? Yes?
T to the negative 1, T to the I, T to the negative 1.
Yes, can you stand back paper, please? So then in this case, you have 4 solutions, right? So the first one is T to the R1, which is T. The second solution is T to the R2, which is T to the power minus 1. And this is 1 over T. The next solution is x to the I, and the last solution is x to the power minus I. All right? You just take t to the power all of those numbers, and then you get 4 solutions. R1 is 1, so the first solution should be t. R2 is minus 1, so the second solution should be 1 over t. R3 is I, so the third solution should be x to the I, and the last one should be x to the power minus I. So now I have to analyze x to the I. The first solution, right? T to the I. Oh, sorry, t to the I. Right, so the x3 is t to the I. I have to analyze this solution. What can I do? We use the same trick with the, yes?
We could write t as e to the line, t to the I, and then we could use Euler's formula
Yes,
to
you
get
can
rid
stand
of
back
that.
paper, please. So again, you use the same trick with before, right? So this is e to the log t to the I, right? Because t is e to the log t. So in this case, this is e to the I log t. So what is the meaning of this expression? Yes?
Cosine of P
Yes.
plus I sine of.
Can you stand back paper, please? So now you're gonna use the Euler formula. So you have cosine of log t plus sinus of log t, right? And then I'm gonna analyze the next solution as well. T to the power minus I. So how can I analyze this solution? Yes.
Wouldn't it end up being the same thing except it's minus I to the sine?
Yes, can stand back paper, please. So you do the same thing. So t will be e to the log t, and I have minus I. So this is e to power minus log t, and this is cosinus log t minus I sinus of log t. All right? Now, I don't like the I in my solution. What can I do now? Like in the previous case. So as in the previous case, I don't like the I here. What can I do? Yes?
Could you potentially sum the 2 solutions? Because the linear combination of 2 solutions is also a solution to the
All right.
equation.
Can you stand back this? So because the linear combination of the 2 solutions is also a solution, right? Linear combination of x3 and x4 are also solution, right? So you can take the sum of x3 plus x4 over 2 is cosinus of log t plus log t plus I sinus of log t plus cosinus of log t minus I sinus of log t divided by 2, right? What is the result of this expression? So if I take the sum of x3 and x4 and I divide it by 2, yes?
Just cosine of log t.
Yes, can you send it back paper, please? So this is cosinus of log t. Is also a solution, right? So, so I can take the average of the two solutions and I get cosinus of log t, and this is also a solution because the linear combination of two solutions is also a solution, right? Now, how can I get the sinus?
You may multiply by I to both equation and minus the.
Yes, can you send back paper, please? So you take x3 minus x4 dividing by 2i. Right. So when you take the difference of the two solutions, I have cosinus of log t plus I sinus of log t minus cosinus log t plus I sinus of log t dividing by 2i. So I have 2i sinus of log t dividing by 2i, and this is sinus of log t, right? So now, so this is also a solution because it's a linear combination solution. This is also a solution because linear combination of solutions are solutions, right? So you can take the sum and you have cosinus and you take the difference and you have sinus. So basically, the fourth solution will be x1 is t, x2 is 1 over t, x tilde 3 will be cosinus of log t, and x tilde 4 will be sinus of log t. Right? So I said that x3 and x tilde 3 and x tilde 4, they are linear combination of x3 and x4, right? So can you express x3 and x4 in terms of x tilde 3 and x tilde 4? So are x3 and x4 linear combination of x3 tilde and x4 tilde? You see that, okay, this is x3 tilde, right? x3 tilde is a linear combination of x3 and x4. x4 tilde is a linear combination of x3 and x4. The question is, are x3 and x4 linear combination of x3 and tilde and x4 tilde? Yeah, why?
Yes, because for example, x3 equals x3 tilde plus I x3.
Yes, so it's simple as this expression, right? Can you sign it back for it, please? Yes, because x3 is x3 tilde plus I x4 tilde, and x4 is x3 tilde minus I x4 tilde, right? So this is simple, right? So x3 tilde and x4 tilde are linear combination of x3 and x4, but x3 and x1 are also linear combination of x3 tilde and x4 tilde, right? So the general, what is the form of the general solution? I have x1, x2, x3 tilde, x4 tilde. What is the general solution? Yes?
Don't we just multiply each of our solutions by a constant and then
Yes.
sum them together?
Yes, can sign back of this. So you're gonna linear you have a linear combination of all of them, right? Right. So to get a general solution, you just take a linear combination of all of the four solutions, and you get a solution of the full equation. The general solution, right? Any questions? So this is the last question in the exam. Right, so if there's no questions, let us go to another exercise. So in this case, you have a similar solution, which is t cube x 4 plus t 4 x 4 6t cube x3 plus 9t squared second plus 3tx prime plus x is equal to 0. Right, so the next example is something similar. You have 4 times x, 4 derivative plus 6t cubed, x3 derivative plus 9t squared, x second derivative plus 3 tx prime plus x is equal to 0. All right? So how do we solve this equation? Yes?
Well, we'd like a characteristic equation that's independent of t. So what we're going to do is look for special solutions of the form x equals t to the r, because then when we take the derivatives, the t's will cancel.
Can I say the back paper, please? Right. So we're going to use the same method, the characteristic equation, and the reason is that because if x is of degree r, then t to the 4, x to the 4 is plus second is of degree r, and t cube x 3 derivative is also of degree r, and t square x second is also of degree r, tx prime is also of degree r, and x is of course of degree r, right? So basically the reason is the same. Like in the previous exercise, the reason is that if x is a polynomial of degree r, then this is of degree r. Like in the previous example, this guy is also of degree r, this is also of degree r, and everything is of degree r, which means that you can, this equation has a characteristic equation, right? So the criteria is the degree of all of the polynomials, all of the terms. Right. Right, so now suppose that x is t to the r, I have to compute 3tx prime is equal to 1. So if x is of the form t to the r, what is 3tx prime? Yes?
It will be 3 times t times r times t to the r minus 1.
Yes, can I say please? So this is 3 times t times r t to the r minus 1, right? So x prime is rt to the r minus 1, so this gives you 3t rt to the r minus 1. And this is basically 3r t to the r. All right, so the next term will be 9t squared x second. What is it? Yes?
It would end up being 9 times r minus 1 times t to the r minus 2 times
Yes.
t squared.
Yes, can you stand back like this? So this is t squared, right? So and this one is r minus 1 t to the r minus 2. And this gives you 9 times r minus 1 t to the r. All right? This is because the first derivative of x is r t to r minus 1, which means that the second derivative of x is r minus 1 t to r minus 2. Multiply that with this square, you get 9r minus 1 t to the r. The next term will be 6 times t to the r x to the power. Third derivative, what is it? Yes?
It would be 6r times t to the cubed times r minus 1 times r minus 2 times t to the r minus 3.
Yes, can you say it back paper, please? So this is 60 to the power 3. And so you just stack a derivative of this guy, right? The derivative of this guy is r minus 1, r minus 2, t to r minus 3, right? And so you combine x cubed with x with t to r minus 3, and you get 6 r minus 1, r minus 3, t to the r. All right? It's good. Explain again. So you have x is t to the r. So the first derivative of this guy is r t to r minus 1. So the first term is 3r t to the r. You take the derivative of this guy, you get x second, and this is r minus 1 t to r minus 2. And this is the result of the second term. Now you have to take the third derivative of x, which means that you have to take the derivative of this guy, which is r minus 1, r minus 2, right? And this gives you 6r, r minus 1, r minus 3. Questions? Right. So now I have to compute the last term. What is it? Yes?
It would be r times r minus 1 times r minus 2 times r minus 3 t to the
Yes.
4.
Can you set back to the top, please? So this is t to the 4, r minus 1, r minus 2, r minus 3, t to r minus 4, and this is r minus 1, r minus 2, r minus 3, t to the r. All right? Now I have to take the sum of everyone. So I have t to the 4x for derivative plus 6t3 x3 plus 9t squared x second plus 3x prime plus x. And this gives you r minus 1, r minus 2, r minus 3 t to the r plus 6 times r minus 1, r minus 3 t to the r plus 9 times r minus 1 t to the r plus 9 times t to the r plus t to the r, and this is 0. This is 3. All right? Questions? It's good. So now what you have to do is you put everything that you just computed here. So t to the 4x 4 will be this guy, right? So you replace t to the 4 x4 with r minus 1, r minus 2, r minus 3, t to the r. You replace the second guy with this guy. right? You replace the third guy with this guy, and you replace tx prime with this guy, and x you wanna replace it with t to the r, right? So what is the next step? Yes.
We want to factor out t to the r so we can get our characteristic equation.
Yes, can say back of this. So now I can factorize. I can put t to the r as the common factor. So I have t to the r minus 1, r minus 2, r minus 3, plus 6 times r minus 1, r minus 3. Right? So r minus, no, 6 times r minus 1, r minus 2. And then I'm gonna put 9 times r minus 1. Right? So plus 3 times r plus 1 is equal to 0. All right? So, so what is the next step? Yes?
I mean, you still need to divide by TR on both sides.
Yes, you can send back to this. So now what you do is you divide both sides by t to the r, right? And you get a characteristic equation. So this is the characteristic equation. Since it's independent of t. Independent of t. All right? It's good. All right. So, so the next step is to solve this fourth order algebraic equation. What we have to do is you have to factorize out everything, and after that you have to solve it, right? So let us do it. So you're gonna have r minus 1 will be. So what is the form of r minus 1? Yes.
Is it just r squared minus r?
Yes, can stand back paper, please. So this is basically r squared minus r. So what is r minus 1, r minus 2? Yes?
Well, the second two terms will come out to be r squared minus 3r plus 2, and so then we multiply each one by r, so it'll be r cubed minus 3r squared plus 2.
Yes, can stand back paper, please. So this is r squared minus 3r plus 2. This gives you r cubed minus 3r squared plus 2r. Right? Now I have to factorize the last term, r minus 1, r minus 2, r minus 3. All right? To do that, I'm gonna group the first guy and the second guy. R minus 1, r minus 2. All right? So what is r minus 3? Yes?
R squared minus 3r.
Yes, can start back to this. So this is r squared minus 3r. So what is r minus 1, r minus 2? Yes? Can you sign back paper, please? So this is r squared minus 3r plus 2. So, what is the, how can I factorize this term? How can I develop this term? So I can, so this guy, I'm gonna write like r squared minus 3r squared plus 2 times r squared minus 3r, right? Right, so you can think of r squared minus 3r as one term. So you can factorize that like r squared minus 3r squared plus 2 times r squared minus 3r. So what is this square? Yes?
R to the 4 minus 6r cubed plus 6r squared.
Yes, can sign back paper, please. So for this is r4 minus 6r cubed plus 9r squared. And I develop this guy, I have 2 times r squared minus 6r. So basically I have r4 minus 6r cubed plus 11 r squared minus 6r. All right? All right, so I explain again. So you have to develop everything right, to get an equation that you can solve. So this guy will give you r minus 1. This is r squared minus r. The second guy is r minus 1, r minus 2. This is r squared minus 3r plus 2. And this is r cubed minus 3r squared plus 2r. So the last guy will be, this is the most complicated guy, so you have to be a little bit clever. What you do is you group the first and the last, and second and the third. You have r minus 3, r minus 1, r minus 2, right? This gives you r squared minus 3 and r squared minus 3 plus 2. Right, so this is, so r squared minus 3 is the similar term between in the product. So you can factorize everything. You have r squared minus 3r squared plus 2 times r squared minus 3r. So this gives you 4 minus 6r cubed plus 9r squared. This is 2r squared minus 6r. So at the end of the day, you get r4 minus 6r cubed plus 11r squared minus 6r. Okay. Right. So now we're gonna put everything together, right? So you're gonna have r minus 1, r minus 2, r minus 3, 6r minus 1, r minus 2 plus 9 r minus 1 plus 3r plus 1 is 0, right? Now I have to put everything that I just computed to this equation. So the first guy is r4 minus 6r cubed plus 11r squared plus minus 6r. So this is this guy. This guy is the one that I computed here. So this gives me 6r cubed minus 18r squared plus 12r, right? So this is basically the terms that I computed here. All right, so 6 times that term, so you have 6r cubed minus 18r squared plus 12. Now, this guy is this term. So we have 19r squared, 19r squared minus 9r. And then you have plus 3r plus 1. And this whole thing is 0. Right, so how can I simplify this whole expression?
combine the like terms,
Yes. So the first one is 1.
just r to the
4.
4.
Yes. So the first one is r to the 4. The second one is
The r cubes would be 0, the r squareds would be 0, and then it
Yes.
would be 30r, like minus 30r.
yeah. So can you say it back please? So the next term will be r cubed with r cubed, right? So you have 0 r cubed. So the next one will be what? Yes.
Will it just be, because 11 plus 9 would be 20 and then minus 18, so it would be 2r squared?
Yes, just add back paper, please. So here you have 11, right? So you have 11 and 18 and 9, so this is 2r squared. Right? So what is the next term? Yes?
Would the r's end up being 0, so the next one would be 1.
Yes, can you sign the back paper, please? So now the next term will be all of the r, right? But when you add everything, you're gonna get 0. So this is 0r. Right? So the next term will be minus 6 plus 12 minus 9 plus 3. This gives you 0r. So the first order term will be 0. Right? And the last one will be? Yes?
Just plus 1.
Yes, inside back paper, please. And this is plus 1. And this should be 0. Alright? Right. So how can I solve this equation? Yes?
You can factor it, so it would be r squared plus 1 quantity squared.
Yes, can inside back paper, please. So here you have what? You have r squared plus 1 square. Right? So let me write it in a better way. So you have r to the 4 plus 2r squared plus 1, and this is 0. Okay? So this one can be written like r squared plus 1 square is 0. So how many solutions do you have in this equation? Yes?
Do you have two solutions, the negative I and I?
Yes, can you sign the back paper, please? So this guy gives you r squared plus 1 is equal to 0, which means that you have r1 is I and r2 is minus I. Right? So basically there are two double roots, but to find the other solution then. So what are the solution of the differential equation? Yes?
Well, it would be t to the I and t to the negative I, but from the last one, it wouldn't, the answers just be cosine log of t and sine log of t?
Yes. Can you stand back paper, please? So the first solution will be t to the I, which is like in the previous solution you have cosinus log t plus I sinus of log t. So the second solution is t to minus I, and this is cosinus log t minus I sinus log t. Right? So because here you have two solutions, I and minus I, you have two solutions for the differential equation, which is t to the I and t to the power minus I, which is cosinus log t and I sinus log t. And the second one is cosinus log t minus I sinus log t. Right? So how can I simplify this?
we can do the same thing we did last time and take linear combinations of the two solutions in order to get one solution with cosine and one solution with sine.
Yes, can say back paper, please. So then you can do the linear combination to get rid of the I. So this is cosinus of t. And second one will be x1 minus x2 over 2i, and this is sinus of t. What is the general solution? Yes?
It would just be like C1 times the x1 plus C2 times the x2.
Yes, can you send back paper, please? So the general solution will be the linear combination of the two. Right, so this will be linear combination of x1 theta and x2 theta. Right, so this gives you C1 x1 theta plus C2 x2 theta. Right? Questions? Right? So basically, in all of those, so basically, normally you have to have another two solutions, but this is too difficult to find the other two solutions. So you only need to find these two solutions, right? Because here you have. So I in this case is a repeated group. So this is the double root, right? So because this is a double root, one solution is x to the I, t to the I, but the other solution you need to find it using. Yes?
Do you find the other solution? Can you use the rule that we used previously and that you multiply the solution?
What is the mechanism behind that
Oh,
solution?
that's the reduction of order method.
Right. So because this is a repeated root because you have a square here, right? Basically, you have two equations x squared plus 1 is 0. So this guy is a double root. So one solution is x to the t. So the other solution you have to find it using the reduction of order method. This is complicated. So for this solution, I just offered you two solutions, but basically it will have 4. So you can find x3 and x4 using reduction of order. But I don't find it for you because it's complicated, right? So for this equation, this is a order 4. If you have a repeated root, then it's fine that if you then this is fine that you stop with the first solution. That you don't have to go further to find the second solution. But in principle, the second solution can be found by reduction of order method. Questions? It's good. Right. So the next thing that I want to show you is how to transform this equation into a different equation. Right, so you have a t squared dx dt plus bt dx dt plus cx is 0. This is Cauchy equation. Right, so this is a t squared x second plus bt x prime plus cx is equal to 0. Right? So this is the Euler-Cauchy equation that you can solve using the method that I mentioned to you. One thing that you can see from all of those three cases is that whenever you see a t, you can replace it by a log t, right? In the three cases, you replace t by log t, right? So in the three cases, there's an analog between the solution, the three cases for the constant coefficient equation, and these are the Cauchy equation. The similarity is that you replace t by log t, right? Now, what happens if I do the change of variable from the first place? So, what happens when we do the change of variable from the first place? Right? Remember that in all of the three cases, I said that there's an analog between the previous equation with constant coefficient and this Euler equation. The analog is that whenever you see a t, you can replace it by a log t, right? So this is something mysterious, and why is it? So let us see what happens if we change the variables right in the first place before doing anything. Right, so we define a new variable. Y is equal to log t. Right? So we're gonna, and we find an equation for y. So now x now becomes a function of y. So what is the new equation for? What is the new equation for x? For x. Yes?
So are we saying our previous equation was x is t to the r? Or are we saying if x is a function of t?
No, I'm just looking at this equation. A t squared x prime plus b t x prime plus c x is 0, right?
Mm-hmm.
Now I define a new variable y is equal to log t, which means that t is equal to e to the y, right? So I have xt now become xe to the y, right? Because so this is the y, right? So this is the y. Because in all of the steps that we solve in the three cases, we see that if you replace t by log t, then you can use the methods of the constant coefficient equation, right? Now, what I want to do is I want to do an experiment that I change variable from the first place, right? So I define a new variable, which is y is equal to log t. Y is equal to log t means that ty is equal to e to the y, which means that xt is now xe to the y, right? So what is the derivative of x in terms of y? Yes?
Just x, y, e to the y.
X, y, e to the y. So you mean this is x prime e to the y? Yes?
If you take, you have the derivative of dx with respect to dt, and you multiply it by the derivative of dt with respect to dy, you'll get the derivative of dx with respect
Yes,
to
so
dy.
this is the chain rule. I just had like of this, right? So first you have to take the derivative of x, and second you have to take the derivative of this guy in terms of y, right? So you have to take the derivative of this guy in terms of y. This is the chain rule. right? So x is now a function of what, right? So dx over dy, dx over dy, dy will be, first you take the derivative of x, and then you take the derivative of this guy inside, right? So this is the chain rule. Remember that? So you have a function f of g of y will be, you take the derivative of everything. This will be the derivative of f prime gy prime g prime of y, right? Or d over dy of f gy will be f prime of gy times dg dy. All right? This is chain rule. So what I do is I replace t by e to the y, and I have to take the derivative with respect to y. So what I do is I take the derivative of x first, and then I take the derivative with the guy inside, which is this formula over here. So what is the final result of this? Right, so I explain again. This is basically the chain rule, right? You take the derivative with a function f of a function g of y, right? So what you do is you take the derivative of function f, which is the normal derivative, which is x prime, and then you take the derivative of g with respect to y. So here I do the same. I take x prime and I have to take the derivative of e to y with respect to y. What is it? Yes?
The derivative of e to y with respect to y will just be e to the y.
Yes, it's just e to y. Right, so this is e to the y, x prime, e to the y. All right? So what I have is that dx over dy is e to the y, x prime, e to the y. Right? And what is it? Yes?
Do we want to write this back in terms of t? So we see that e to the y is just equal to t, so it will just be t times the derivative of x.
Right. So you remember, can you stand back please? So you remember that t is e to the y. So this is nothing but t x prime of y. The tx prime of t, right? So I explain again. So in all of the solution that I gave you from the beginning, you have a remark that whenever you see a t, so you have a remark that okay, there's a similarity between the Euler equation and equation where you don't have you have constant coefficient. That is, whenever you see t, you cannot replace it by log t, and you go back to the previous case. So I'm gonna do an experiment to see what is going on if I replace. I put a new variable for log t from the first place before doing any solving, right? So what I do is I put y to be log t, which means that t is e to the y, all right? So xt in this case will be x e to the y, right? So this is standard, right? So for instance, so this is the process that I have. For instance, if I have a function xt is t cubed plus t squared, right? Now I do a change of variable. I put t to be e to the y, so the new x e to the y will be e to the y to power 3 plus e to the y. Something like that, right? So what I do is that I put a new variable, y is log t, and then t in this case will be e to the y. I plug it back to the equation, and x to the xt will be x e to the y, like here, right? So if I have example, if I have xt is x cubed plus t, I replace t by e to the y. So I have e to the y3 plus e to the y. I'm going to take the first derivative of this guy. So the first derivative can be computed by the chain rule, right? So dx dy will be x prime, and then I take the derivative of the guy inside. The guy inside is e to the y, so the derivative of e to y is e to the y. All right? So this is basically the chain rule. But I see that here I have e to the y and e to the y, so I go back to t. I have tx prime t. It's good. Right, so now I'm going to take the second derivative. So I want to take the second derivative of the whole thing. Right, so I have d dy of e to the y, x prime e to the y. What do I get? The first thing that I have to do is which kind of rule should I use? Yes?
Chain rule.
Not yet.
Product.
Yes, can you stand back please? So I'm going to use product rule, right? So this is a function of y. And so I'm going to do the product rule, right? So I'm going to take the derivative with respect to the first function, e to the y times x prime e to the y plus e to the y d over dy of x prime e to the y. All right, so this is product rule. You have what? You have f g y g d over dy is d over dy of f times g plus f d over dy of g. All right. So you take the derivative of product. How do you do it? You take the derivative of each of them, and then you multiply with the other guy, and you take the sum. So in this case, you have this is f and this is g. This is my f and this is my g. I take the derivative with respect to both of them. I get d over dy of e to y times g prime. So I have times g. So this is x prime e to the y. And the second guy is f times g prime. So I have e to y and dy. X prime is e to the y. All right. Right. So what is the result of the first term? Yes?
It would just be e to the y times x prime e to the y.
Yes, you can sign it back paper, please. So the first guy gives you e to the y, x prime e to the y, right? What is the second derivative? Yes?
Okay, for the second derivative itself is just x double prime e to the y times e to the y, and then since there's another e to the y there, you multiply that together. So it's x double prime e to the y times e to the y.
Yes, can sign and back paper, please. So you do exactly like here, right? So you use the chain rule. So you have e to the y, x second e to the y, d over dy of e to the y. So this gives you e to the y, x prime e to the y plus e to the y, x second e to the y. So this derivative gives you e to the y. So finally you have e to the y, x prime e to the y plus 2e to the e to the 2y, x second e to the y. All right. So now I take the second derivative of x. I get d over dy of e to y, x prime e to the y plus e to y times the d over dy of this guy. So to take the derivative of this guy, I'm going to use again the chain rule. So first I take the derivative of this guy. So this gives me x second, and the second one is the derivative of e to the y, which is e to the y. So I group the first and the second guy. I get e to the 2y. Now, if I want to come back to the original variable, how can I do it? Yes?
Just replace every e to the y with t, so it'd be t x prime of t plus t squared x double prime of t.
Yes, can I back paper? So here I have t x prime t plus t squared x double prime of t, right? So I replace e to the y by t. So this is x t prime of y plus t squared x double prime of t. Now I put everything into the so now I put everything I just computed into the form that I have. So I have d squared dy is equal to t squared x second t plus t x prime t. Right? So now let's focus about the t here. And then you have dx dy is equal to tx prime. All right? So this is nice because here you don't have the t, right? So you just have a pure derivative, and here you have t squared and t. This is very nice, right? Right, so now how can I derive a differential equation for x with the new variable y? So I want to have a new equation for dx dy instead of dx dt. Anyone here? Yes?
The bottom equation for dx dy is equal to tx prime. Could we write x prime as dx dt and then cancel the dx from both sides, and you can't do that?
Yes?
So I guess one way you could put the dx dy into the second derivative and then plug that second derivative into
Yes.
the original equation.
And stand back paper, please. So this is something that you should keep, and you plug it back to the first equation, right? So what do you get? You get d squared x over dy squared is t squared x second. So I plug this guy here, right? So I'm gonna have dx over dy right? So this is a system that I have. I have the second derivative of x with respect to y will be t squared x second plus tx prime, and dx over dy will be tx prime, right? So I have tx prime in terms of dx dy, but I want to express t squared x second in terms of dx dy. So what do? I replace tx prime by dx dy. So I have it here. So dx dy squared is t squared x second plus dx over dy, which means that t squared x second is equal to d squared y squared minus dx dy, and dx prime is now dx dy. Now you start seeing the equation for dx dy. What is it? Right? So from the previous computation, I have dx over dy is tx prime, and dx d square x over dy square is t square x second plus tx prime. I plug this into the equation. I found that dx d square x over dy square is t square x second plus dx over dy, which means that the t square x second is, I just plug this guy to minus to the other side, so I have d square x over dy square minus dx over dy. Now I start seeing the equation for dx dy. How can I get it? So one more remark, you have what? Xt will be the same with x e to the y, right? It doesn't change anything. So x is equal to x. So let me keep it right. So how can I get the equation? Yes?
Would you set like the first equation equal like dx over dy, and then that equals like the d squared x dy squared minus the t squared x double prime, and then you set that equal to your other equation for dx over dy?
So I have right away the equation. So what is it? What is the new equation? For what? Yes?
So, just so here, we're just trying to like rewrite the original Euler equation. So it would be a d second derivative d minus the first derivative. Pretty much plug in the t squared x double prime.
Yes, can you sign
into the
back?
first.
Can you sign back of this?
And then do the same for the second.
Yes, this is very smart, right? So you plug this here, and then you plug this here. This is very smart. You can add 5 times. So you said that this is 5 times because this is very smart, right? So what I do is what I can do is the following. I have t squared x second, and I have tx prime, right? I plug everything into the equation. So what I have is a d squared over dy squared minus dx over dy. And then the second guy will be b times dx over dy. And the last time I keep it the same. Right? Right? So I just replace tx second by dx over dy squared minus dx over dy into this equation. So I have a dx d squared x over dy squared minus dx over dy. Tx prime will be dx over dy, and then the left over is x. And what can you say about this equation? Right, so can I simplify this equation? Yes?
You can multiply the dx dy times a, and then you can write it as b minus a times dx dy.
Can you say it back paper, please? So this is a d squared x over dy squared minus a dx over dy plus b dx over dy plus x, and this is 0. So a over dy squared plus b minus a dx over dy plus x is equal to 0. This is the equation for y that I have. What can I say about this equation? Right? So I plug this back into the equation. I have this equation. So I have so this term is going to be a dx over dy squared minus a dx over dy, and this is b dx over dy. This is x. I group b minus a, so I have b minus a dx over dy plus x. What kind of equation is it?
Since we turned t into y, would this be the characteristic?
No, this is not yet. This is not the kind of. I'm asking, what kind of differential equation is it?
Would it just be a second order linear homogeneous?
And there's one thing missing. Second order linear homogeneous. What else? Yes? Yes. Can you stand back a bit, please? So this is second order linear homogeneous with constant coefficient, right? So this is second order linear constant coefficient. Right? So the magic here is that when you put a new variable, you get a, so this is non-constant coefficient, non-constant coefficients, right? So this is a non-constant coefficient, but when you put a change a variable y to be log t, you get a second order differential equation, homogeneous with constant coefficient, and you can solve it by the characteristic method. And then after you solve it by the characteristic method, you have three cases. Whenever you see y, you can replace it by log t, right? This is why there's a similarity in the formula that I showed you last time. Whenever you see a t, you can replace it by a log t. The reason is because you can transform this non-constant coefficient into a constant coefficient equation, right? So to summarize what I have done so far, this is the so given an Euler-Cauchy equation, t squared x second plus b t x prime plus cx is equals 0. So this is non-constant coefficient. So if we put y to be log t, t is equal to e to the y, we add a new constant coefficient. Equation a dx dy plus b minus a dx dy plus cx is 0. The second equation can be solved by the characteristic equation. AR squared plus B minus AR plus C is 0, right? And after that, you replace, this is the characteristic equation of this guy that we found from the previous time. So you see again this characteristic equation, right? We can solve 2 instead of 1 and replace y by log t in the final result. All right. So to summarize, so given a Cauchy-Euler equation, if you change the variable y to be log t, or t is e to the y, you get a second order differential equation with constant coefficient. So this is non-constant, but this is constant. So this equation has a characteristic equation. You solve it in a standard way, and at the end you replace y by log t, and you get a solution that you want. All right.